Ladies and gentlemen, class recording started. So, up on the board is our calendar for the remainder of Unit 4. We'll see how closely we stick to this. But so today, the 6th here, right, we'll do Introduction to Vectors. A lot of the ideas that we talked about on Friday when we did Mr. Toad's Wild Ride around Centerville, we will look at those a little bit more, talk about the theory behind them, do a couple of sample calculations just to get us up and rolling. Tomorrow, we are actually going to spend the day just doing some practice problems, reinforcing the concepts that we're going to introduce today. So I'll just give you a couple problems from the book, have you work on them, make sure that we're comfortable with these ideas, how to get this, how to get that, et cetera, et cetera, et cetera. The rest of this week, we will continue working on vectors and what does it mean when we, what does it mean to add vectors, what does it mean to add quantities that are vectors, because we can't just add the numbers together. We'll see how that goes later on. This then eventually gets us into next week when we start getting into projectile motion. So chapter 4 is actually about motion, but it's motion in 2 dimensions. And so we'll look at that starting off today. How do we deal with things in 2 dimensions? And then we'll apply those ideas specifically to motion starting next Monday. Your test for Unit 4 is scheduled for October 27th. So that'll be 3 weeks from today. You got a couple of off days in there and one late start day. So yeah, it's gonna be we got some things spaced out a little bit. But that will be your last grade for the first grading period. So that'll be last grade there. Okay, good. We'll have a couple of open note quizzes thrown in there. I'll kind of add them in maybe the day before, so we give you a little bit of notice. I won't spring it on you the day of the quiz, but just there will be a couple of quizzes thrown in there just to make sure we're keeping up with the stuff that we're supposed to be keeping up with. Okay. I added this morning that's here 1 week from today on the 13th. Your Unit 3 test corrections are due, so obviously you can turn them in before that if you'd like. Just whenever you're done, tuck them inside your test, right, and throw them in the tray on the side. Okay? Good there. All right. So I start today. Yeah, go ahead. Yeah, that's the next day that we're doing like custom review. So that's I'll look to that because mine is version. All right, I'm going to start today on page 112 of your book, if you want to open there. If you don't, it's okay. You actually have these pictures on the front of your packet that I gave you today, but it starts on page 112. So, chapter 4, as it says here, it says motion in 2 dimensions. So like I mentioned before, chapter 4 continues to be about motion, and it's actually a continuation of the kinematics ideas that we introduced in chapters 2 and chapter 3. So we're still dealing with displacement, we're still dealing with velocity, we're still dealing with acceleration. But as you can see from this picture of the tennis ball bouncing as it goes across the floor, we have to account for more things in this chapter because as things, the real world does not exist in 1 dimension. The real world exists in 3 dimensions. The concepts are much easier to introduce in 1 dimension, but that doesn't mean we can't apply them to 3 dimensions. We're not going to jump straight from 1 dimension into 3 dimensions. We're going to stop at 2, but those ideas, expanding them from 1 to 2 is similar to expanding them from 2 to 3. But if we look at this tennis ball, right, as it's bouncing along, if we look at its motion from here to here, to here, to here, to here. Some similarities between what we see in this picture and what we saw in the last chapter, right? For example, what do you see about the spacing between the tennis balls as it's bouncing upward? They're getting closer, because what's happening to the tennis ball as it's moving upward? It's slowing down, because gravity's pulling it in the other direction. But on its down trip, right, from here to here to here to here to here, right, those balls are spacing out. Just like in the last chapter, because now gravity's pulling it down, right, and it's increasing the speed, and that causes it to travel a farther distance. So there are some similarities there, but first we have to deal with what makes it a little different. Down here, the big idea of chapter 4, it says, horizontal and vertical motion of an object are independent of one another. And while that's true, we still have to account for both of them. So section 4.1 gets into how do we account for these different motions that might be occurring at the same time. Okay? Good there. All right. So I start you with an oldie but a goodie. Elise would be disappointed that she wasn't here to see it.
I'm applying for a new film loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out my new weapon. Piranha gun! Oh yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. You want a demonstration? Oh! Ah! It's so difficult sometimes to get blind back inside.
So, alright. So today, as we get into section 4.1, we deal with vectors in physics. Okay? We've introduced the concept of a vector before. We introduced it back in chapter 2. Right? We said that a vector is going to tell us two things, right? It's going to tell us magnitude and direction. Right? The direction part, that's pretty easy. It just tells you which way something's going. The magnitude, we said, tells us how big or how much of something we're talking about. Okay? We have to have a way, especially for the direction part, to tell which direction. Because if you look on page 1 of your packet, bottom left-hand corner, which is actually on page 114, right, of your book, over here on the left-hand side, figure 4.1, which you guys have in your packet as well, okay, similar to a problem that Fenwick had in the lab on Friday. The first question says, Fenwick tells the cab driver that he wants to go to a place that's 12.5 miles away from his house. And using the ruler to measure off 12.5 miles, I think there were actually 3 places that were 12.5 miles away from his house. So where do you want to go? Or like figure 4.1 says here, if you only know that the library is 1 kilometer from where you're standing, it could lie anywhere on a circle that has a radius of 1 kilometer. That leaves a lot of possibilities for where the library could actually be. But if you are told that the library is 1 kilometer northwest, now we get more into deciding, okay, now we know more the precise location of that library because we have how far away it is, but also which direction it is from our location. Okay? In 1 dimension, direction is easy, right? Because how many options do we have in 1 dimension for direction? 2. You go this way or you go that way. And we distinguish those because we call one positive and we call the other one negative, okay? But when we get into 2 dimensions, those possibilities increase. So we have to describe the direction of our vectors in a little different way than just positive and negative. Before we move on though, so key point, and this is in your packet, right? It says here, a vector, you're watching the recording, sorry. Key point, you have this in your packet. It says, a vector is a quantity that is specified by both length and a direction. The length of the vector is referred to as its magnitude. How much of something, right? And then, just like Vector said in the little clip that we watched, right? We generally, like it says here, representing vectors, we indicate a vector on a diagram, we draw an arrow, because the arrow, the direction the arrow points, represents the direction. And then we try as much as we can to make the length of the vector representative of its magnitude. We don't have to be perfect with it, but the closer we are to drawing it to scale, the more representative it is of the actual situation. In the lab that you did on Friday, everything was to scale because you were using a map and you used the ruler, so the lengths were fine. But drawing everything to scale can sometimes become tedious. So we don't have to, but if we can at least somewhat use the lengths of those vectors to represent the magnitude of them, that makes our lives a little easier. Okay. Good there? All right. Real quick, just to hit these initial points home. On page 114 of your book, there are practice problems number 1 and 2. So these shouldn't take real long, but just, to make sure we enforce them. I'm sorry, I didn't put these in your packet. I apologize for that. So, yeah, I didn't put them there. So this is on page 114. All right, so number 1 says, for each of the following quantities, indicate whether it's a scalar or a vector. We talked about the differences between scalar and vector back in chapter 2. That concept does not change. All the things that were scalar back in chapter 2 and chapter 3 are still scalar. All the things that were vector back in chapter 2 and chapter 3 are still vectors. So, here, if we first talk about the scalars, sorry, let's talk about the vectors first. I'll give you a hint. 2 out of the 4 are vectors. Which ones are the vectors? No. B is definitely a vector because it's asking us about displacement. And displacement was a vector in chapter 2, right? It's still a vector here in chapter 4, even though now we might be talking about it in 2 dimensions, right? And then the other vector quantity is C, right? Because it's asking us about velocity, and velocity is also a vector quantity, right? It has to tell us not only how fast something is going, but also which way that it's going. And then that leaves us, right, with the scalars. Right? Time's going to be a scalar, okay? There's no direction on time, it's just how much time elapses, right? But then also, average speed going to be a vector as well, because average speed only tells us magnitude, which in case of speed tells us what, Krista? The magnitude of speed tells us, well, what does speed tell you? It tells you how fast you're going, right? So the magnitude in this case tells us how fast, right? But if we go to velocity, that then tells us also not only how fast we're going, but also which direction as well. Okay? Good there? All right, and then chapter 2, or practice problem 2, it says rank the vectors in figure 4.2 in order of increasing magnitude. I really wish that they hadn't, like, given you this blatant hint, right, of this problem, okay? But, right, even if we don't have that hint, we said that if we draw arrows to represent vectors, the magnitude is represented by its what? What tells us about the magnitude of the vectors that we have drawn in this picture here? The length of the arrows, right? So, if we go rank the vectors in order of increasing magnitude, which one has the smallest magnitude? B has the smallest magnitude, and then C has the second smallest magnitude, and then A is third, and then D is fourth. No regard for what direction they're pointing, only how long the arrows are. Good there. Okay. Next, again, not in your book, I really wish or sorry, not in your packet, I really wish I would have put it in your packet, but I didn't. On page 115. So if you want to open your book, page 115, figure 4.1 on 114. Okay. We illustrated the idea that if you just tell me the library is 1 kilometer away, that gives a lot of possibilities about where the library is. But if I know that it's 1 kilometer northwest, now I know exactly where the library is. Even though I may know exactly where the library is, sorry, this question. So this arrow right here, R on that, or the one that's labeled R here, which is the same arrow as this R right here, what would that represent? What term is that indicative or representative of from what we introduced back in chapter 2 and chapter 3? That would be your displacement, right? Because it's a straight line from starting point to ending point, right? Now, regardless of how you get there, that's still the displacement. But in real life, we may not be able to take a straight line from where we're starting to where we're ending. Because, like, you know, if we're talking about a city, there's things like trees and houses and fences and cars and stuff like that in the way. But regardless of how we get from the starting point to the ending point, if we're traveling in a northwesterly direction, we can think of that really as 2 trips, 2 separate trips. A west trip and a north trip, or a north trip and a west trip, right? Northwest means we're doing 2 things basically at the same time. We're going northerly and we're going westerly. It really doesn't matter whether you go west first and then north, or whether you go north first and then west, you end up in the same spot, displacement-wise, okay? But this illustrates, or this introduces us to the idea of what we refer to as component vectors. Every vector in 2 dimensions is really a combination of 2 smaller vectors that occur in the same direction as the total vector, right? So this trip right here, from where you start to the library in the northwesterly direction, is a west trip and a north trip. Those 2 separate trips we refer to as the components of the total displacement. This would be the westerly component, and this would be the northerly component. Okay? Every vector we can break down in that way. And we refer to that as resolving the vector into its components. So key point. To resolve a vector means to find its components. A vector's components are the lengths of the vector along specified directions. It's going to be a lot easier in many instances, especially if we have multiple vectors, to examine their components as opposed to the actual vectors themselves. In Fenwick's Wild Ride, you had to do that for like the first 4 trips, right? And you used your ruler to measure the up and down component and the side to side component, right? And then we called them positive or negative, depending on whether they were east or west, or right? You were finding the components. The combination of those 2 components gets you the actual vector. Down at the bottom of page 115, you have this picture actually on the 2nd page of your packet. Here's figure 4.4, and 4.4a gives you a displacement vector. What's the magnitude of that displacement? 1.5 meters, right? And then the direction they have given to us as an angle in relation to the positive x-axis, okay? On the lab that we did on Friday, the compass rose on the map led us in, or we sort of used that like a unit circle, right? 0 degrees east, 90 degrees north, 180 degrees west, 270 degrees south. A lot of times your book will do that as well, but giving you angles in relation to the positive x-axis. Okay? Good there? So the direction of 25 degrees means that it's just a little ways up from the positive x-axis. But over here in B, they have resolved that vector into its components. A vector that ends up in the first quadrant of an xy axis, yes? You're going to look at that in math, right? A vector that ends up in the first quadrant of an xy axis has an x component, or a horizontal component, and a vertical component. Both of them are positive, right? Positive x, positive y. Right? That good there? Here, letter B, or picture B, shows you those two components, right? Now, if one of them's along the x-axis and one of them's along the y-axis, what has to be the angle between them? Got a trick question. 90 degrees. If one's on the x-axis and one's on the y-axis, right, they're perpendicular to each other. These two component vectors are perpendicular to each other. Meaning, we can make ourselves a little right triangle, where the two sides of the right triangle represent the component vectors, and the hypotenuse of the right triangle represents the vector itself. What do you know about the hypotenuse of a right triangle compared to the other two sides? What has to be true about the hypotenuse? It always has to be the largest side. So we can use that as a check when we're going to do these things, right, to see if we're getting correct answers just by checking that out. Okay? Now, because it's a right triangle, we can use our right triangle trig identities that we introduced back, I think in geometry. Do you learn about sine, cosine, tangent, or is it algebra 2? I can't remember if it's geometry or algebra 2. But anyway, we can use those trig identities to help us find the sides of the triangle. Okay? For example, on page 116, which is also, 117, which is also page 2 of your packet, down at the bottom of page 2, we have guided example 4.2. Down at the bottom of page 2 of your packet, you have guided example 4.2 without the extra mess. And there it is. And go. Alright, so it says. Oh, sorry. People watching the video, that was sick, no problem right there. Alright, so example 4.2 says need a lift. It says, at a local ski resort, you take a rope tow to the top of the bunny slope, because you are a risk taker. So your displacement vector for this trip has a length of 190 meters and points at an angle of 26 degrees above the horizontal. Totally, yeah. During the ride to the top, how far have you gone in the horizontal direction? How far have you gone in the vertical direction? So, it says, your displacement vector for this trip has a length of 190 meters and points at an angle of 26 degrees above the horizontal. Which line on this picture is representing your displacement vector? The hypotenuse, or the one that's labeled D here in that picture, right? And we know that this hypotenuse has a length of 190 meters, and it told us that this angle right here is 26 degrees. Okay? Good there. Part A asks us about how far have we gone in the horizontal direction. First, are we good with horizontal? Right? Which way is horizontal? Side to side, right? So it's asking us in this question here about d sub x, which is the x component of the displacement. Okay? All right. We know the hypotenuse of this triangle, and we know one angle of this triangle. In relation to the angle that we know, which is 26, right? I'm sorry, we should have done this, right? What does this angle have to be right here? That one has to be 90, okay, because we have an x and a y, and they're perpendicular to each other. So we have a right triangle where we know the hypotenuse and one of the angles. We're trying to find one of the sides. Which side is that in relation to the angle that we know? It's the adjacent side, right? So this is going to be our adjacent side, right? And then that means that this side over here, the y component, would be what side? The opposite side, at least in relation to the angle that they gave us to work with. Okay? So, to find the adjacent side, right, knowing the hypotenuse, which trig function relates adjacent and hypotenuse? Remember? Cosine, right? Remember SOHCAHTOA, right? So, ca, right? Cosine of theta equals adjacent over hypotenuse, right? All right, that's adjacent over hypotenuse. Okay? First, are we good with theta? Right? Theta is just, it's a Greek letter that we use to represent angles. It's just a variable, just like everything else. Okay? It's like x or y or whatever it is. Okay? All right. So we start plugging in things we know. We know that the angle that they gave us was 26 degrees. We're looking for the adjacent side, which is the x component, over the hypotenuse, which they gave us as 190 meters. Okay? Real quick, right? Make sure this angle is given to you in degrees. Make sure that your calculator is calculating things in degrees. If you're not sure how to do that, right, on your graphing, if you have a TI graphing calculator, top left, there's a button that says mode, right? If you hit the mode button, then if you go the third one down on that list, it should say degrees or radians. We're going to be in degrees, okay? That's going to be a problem for those of you that are in calculus because you switch back and forth every day, every period, so, try to remember. So, that's all I got for you. All right. And then we can figure out here that the x component, or the horizontal component, of this 190 meter displacement is 170, if I remember correctly. We round properly? Okay. And is that okay with the fact, does that match up with the fact that hypotenuse has to be the longest side of this triangle? Still good there, okay? Over here, right, how far have you gone in the vertical direction? That's the opposite side of the triangle, okay? We know the opposite side, we're looking for the opposite side. Technically now we know the adjacent side, but sometimes we make mistakes, okay? So let's use the number that they gave us in the problem. Now we want to find the opposite side. We know the hypotenuse, okay? Which trig function relates opposite and hypotenuse together? Sine, right? So, right? Sine of theta is equal to opposite over hypotenuse. We plug things in that we know. Sine of 26 degrees equals the y component of the displacement. The displacement itself is still 190 meters. And if I remember correctly, 87, 83? Go ahead. I think it's like 170 point something, right? Okay. It's 170.7? Okay. So here, this is only 190 is only 2 significant digits. 26 is only 2 significant digits. So we have to make our answer around only 2 significant digits, right? The 1 is significant, the 7 is significant, and we don't have to worry about the rest of it. So even though if we went to 3, we'd have to round that 0 up to 1, but it doesn't ask us to. We can just go 1/7. That's only 2 significant digits. Go ahead. This is all I got, so. If you want actual tissues, you can go see Crystal. But all I've got is these paper towels, so, you know, they're super soft and absorbent. So, you know. All right, good there. Okay. Good, you can go to that. All right. Next, on page 118, which is also the top of page 3 of your packet, you have figure 4.7. And it says, you walk home from school and you cover a distance of 500 meters. But remember, distance is a scalar, okay? It doesn't give you direction. It just so happens that you cover distance 200 east, 300 north. It wants to know the displacement. So if we have the 2 sides of the triangle, we can figure out the hypotenuse using what? Pythagorean theorem, right? Which here in the middle of the page, right? Remember, you have to take the square roots in order to get the actual value of that displacement, okay? And then, if we want to know the direction, which in this picture is already labeled as 56.3 degrees, but to get that, if we know these 2 sides of the triangle, those would be the opposite side in relation to the angle we know, and the adjacent side relative to the angle that we know. So we can use our trig function tangent to relate those 2 together. And I think I gave this to you in your packet, right? Here's our definition of tangent, opposite over adjacent. But the one thing we have to take care of here is we're not looking for tangent theta, we're just looking for theta. So we have to take the inverse function in order to get the theta by itself to get what the actual angle is. So here, right, you can see that they plugged in opposite 300, adjacent 200 in relation to that picture, but then they have to take the inverse of that to get the answer. Okay? All right. Tomorrow, we will spend the day practicing. We didn't get to the example of this, so I'll do the example of this first thing tomorrow. And then we will spend the rest of the time just doing some practice. Finding components, resolving vectors into components, and then finding the overall vector if we know the 2 components. Okay? That's where we're headed tomorrow. So make sure you have your calculator, make sure you have something to write with, and we'll do some practice there. There is a couple homework problems on the calendar for tonight. They are all conceptual about vectors and things like that. So we'll do the problems tomorrow.